Alright, so this next video is a Physics 1 video, but I'm doing it also to just prepare for the Physics GRE. The Physics GRE is a test you have to take if you want into graduate school. Well, not all grad schools require it, but it's something I'll potentially have to take, so doing some old Physics 1 stuff to review. They say you should go through your introductory physics problems to study, so I'm doing that. And in addition, this might be something that helps somebody who's taking a introductory physics class. So as shown below are two carts connected by a cord that passes over a small frictionless pulley. Each cart rolls freely with neglectable friction. Calculate the accelerations of the carts and the tensions on the cord. So this is really begging to do Newton's second law. So the first thing we need to do is draw free body diagrams. I'm going to call this mass 1 and this mass 2, just for notational purposes. So for the first one, for object 1, we can think of a coordinate system. I don't want to go through the number, I want to be able to see it. Like this. We'll call this y and this x. Okay. Now, why did I do this? Well, you can always change your coordinate system. That's up to you. And one of the tricks to doing this is to point one of your coordinate axes, in this case the x-axis, in the direction of your acceleration. You really don't want components of acceleration. It's going to make the problem much more difficult. Now, you don't have to do this. This is just a trick that I did, and it's much easier for me to do it this way. That way you don't have components and you have to deal with the x component of acceleration, and it's just a mess. So trust me, tilt your coordinate axes so that your x-axis is along your acceleration. Okay? Well, in that case, if we think of it like this, our normal force is just straight up. Our tension force, these are forces, that's the tension from the string, is pulling to the right. Gravity is going to pull it down like this. Okay? This is the force due to gravity. And I'm just going to call this theta 1, this theta 2. So this is theta 1. I'm going to solve it as an expression. I don't really want to deal with numbers. I think they're more difficult that way. And that way, if your numbers are slightly different, but it's the same idea, that's even better. Okay, so that's our free body diagram. This is obviously your y component. This is your x component. And this is for mass 1. So nothing too crazy there. For the other coordinate, or for the other objects, we're going to also tilt our coordinates in the same way. Okay. So we'll say that this is your y-axis, and that this is your x-axis. And once again, your normal force is going to be straight up. Your tension is going to be to the left now. And the force due to gravity is going to be like this. This angle here is theta 2. This is the y component. This is the x component for 2. Now, how do I know that angle is that? Well, there's a few ways you could do this. The way that I remember is if you're dealing with a ramp problem, which is the problem I was studying for. Theta is always the angle between your perpendicular. The other way to do this is think what happens if you've taken calculus. The limit as theta goes to 0. Well, when theta goes to 0, what happens? It's basically just a flat piece of, it's not really a ramp anymore. You're flat, you're on the ground. What part of our component of gravity should remain when theta is equal to 0? Well, just the y component, right? Gravity would just pull straight down. Well, that means it has to be not sine of theta. Sine of theta would be, sine of 0 would be 0. That means our adjacent, our cosine, should have the y, since cosine of 0 is just 1. So that's one way to do it. Just in case you're, so this is the limit as either theta goes to 0. You can also just do some exterior angles and whatnot to get there. I like the limit way. I think that's nice. But just so there's no confusion whatsoever, I want to be as thorough as possible. So that is our free body diagrams. And now we can move on to do Newton's second. And if you're doing this for the context of the GRE, don't be this thorough because you're being timed. I would probably just speed run this, but I'm going to be thorough for the moment. So Newton's second. And the way that I like to do Newton's second is I like to break it up into components. Namely my x motion, that's what I want, and y motion. And I'll put this one here because this first one will be, I'll move it down a little bit so it's not cluttered. I just put the one there to remind myself it's the sum of all forces in the x direction on particle 1. That's obviously equal to m, the second mass 1, times the second derivative of position for 1, which is the same thing. Acceleration in the x direction is equal to this. You could write it as acceleration if you wanted, it doesn't matter. So what forces do we have in the x direction for the first one? Well, we have tension minus m1g, and we want this component here. So that's sine of theta 1 equals m1 x1 double dot. For 2, it's going to be this part, which is going to be the same idea, m2 g sine theta 2, and then minus your tension is equal to m2 x2 double dot. Frankly, I'm not that interested in the y motion. You can do it if you want. For 1. And by the same logic, this is the acceleration in the y direction. This, of course, would be 0. You could do that, but I don't think it's really necessary. So, okay, we need to find the acceleration. The trick here is, if we look at this diagram, does it really make sense for them to have different accelerations? Does it make sense for block 1 to accelerate at 5 meters per second squared and block 2 by 2 meters per second squared? Well, not really, because they're attached by this string. Okay? And we're going to assume that this is a frictionless pulley, so we don't have to worry about that, and that this is a perfect physics wire. So obviously, if you had a real physics wire, there might be a little slack or whatnot. You can ignore any issues with that. When block 2 moves, block 1 moves, and vice versa. So, hopefully that is enough to convince you that the acceleration for block 1 is equal to the acceleration for block 2. So I'm just going to make that quick substitution. We'll just call it equal to A, the acceleration. I'm going to solve for tension. I shouldn't have labeled these. Here, let's do this. 1, 2. There we go. So from equation 1 there, I'm just going to solve for tension. Tension is M1A plus M1G sine theta. And now I'm going to plug that into two. So I'm going to take this t value and plug it in there. And when I do that, I get M2G, this is theta 1, sine theta 2 minus M1A minus M1G sine theta 2 equals M2A. And from here, it's just algebra. Obviously, I want to get my A's on both sides. So I'm going to add that over. I'm going to factor out a G. So I have G, M2 sine theta 2 minus M1 sine theta. This should be sine theta 1. M1 sine theta 1, sorry about that. Is equal to, factoring out the A, M1 plus M2. And finally, all you have to do is divide over to solve for the acceleration. Bit ugly, but you know what I'm trying to do. And this is your answer. All you have to do is plug these values in to get the actual numerical value. The question also asks for tension. If they wanted that, now that you know acceleration, you can plug that into here and you can get tension. Now, I'm not really going to actually plug the numbers in. I think the acceleration is like 2 meters per second squared or something. But you hopefully now know how to approach these problems. So hopefully that helped. If it did, please subscribe and please like the video.